Yeah. So thanks so much for organizing this. I'm fairly new to the ML community, so it's nice to finally meet a lot of people in person. And since this is supposed to be sort of a informal thing where we get to know everyone, I decided to speak on something very recent. We just posted it on the archive a couple of weeks ago. And what it is we're continuing sort of line of work with Gerard and Reza, where we've been trying to understand the evolution of stochastic gradient descent in natural high-dimensional problems. And this work with Jiayang as well is trying to understand the joint evolution of the training trajectory, so the evolution of stochastic gradient descent in the parameter space with natural spectra, like the spectrum of the Hessian along the training trajectory. So the motivation for this was, we've been trying to understand this belief that we've heard over the years that somehow the reason why stochastic gradient descent is able to train modern networks, even though they're in high dimensions, even though they're highly non-convex losses, it's because somehow the landscape has many flat directions, and SGD is somehow able to find some hidden low-dimensional structure to then focus its attention on this. So this, my belief is built off of a fairly large body of experimental and heuristic work. One thing that sort of really motivated us is this proposal by Yan Lecan and his collaborators, in particular with Levent Seguin during his PhD, Yan Botu and Yan Lecan, where what they proposed after a lot of numerical investigations is that what should happen is if you train a modern network using SGD, then at some point along the training trajectory, what will happen is, or rather along training, what will happen is if you look at the spectrum of the Hessian of the empirical risk, computed either on the training data or on the test data, if you look at how this evolves along training, what will happen is that the spectrum should have a sort of rich structure. There should be a bulk, which is most of the eigenvalues, and these should be concentrated near zero. But then there should be some outliers. The bulk will be fairly non-universal. It'll depend on the architecture and stuff, but these outliers are supposed to carry the informative structure of the data, and their evolution along training is supposed to be fairly on-true. So there's been many experimental works building this up, and in particular, I wanted to highlight this work of our colleague Barlan Papian, who's at U of T, who showed numerically that this picture holds really at scale. So he trained a modern network architecture, VG11, on a standard benchmark, CIFAR10, with moderate step size. And so here I've taken plots from one of his papers for that setup. On the left, it's the spectrum of the Hessian computed using the training data. On the right, it's the same thing computed using the test data at a point along the training trajectory. And what you see is there's, most of the eigenvalues are near zero, but then there are 10 outliers. And why 10? Naively, you would say, well, CIFAR 10, there's 10 classes, there's 10. And then motivated by this, a group of physicists, Ramgurari et al., proposed that, well, maybe what should be happening is gradient descent should find this top space and spend most of its time evolving there. And they gave arguments numerically and based off of a heuristic analysis of basically multi-class logistic regression. And so our goal for today's talk is, to what extent can we give sort of a rigorous example of this on a, so can we find a natural high-dimensional statistical model of data, a natural model of training multi-layer networks, where we can show rigorously a picture like this occurs. And just sort of, what do I mean by high-dimensional? Right, in the modern era, we're interested in massive models with very high-dimensional parameter space, very high-dimensional data, and our step sizes, we don't want to be arbitrarily small. We need them to be somewhat large. We don't want to burn through our whole data set. And so in this regime, the sort of theory is very different from the classical asymptotic theory of statistics. And this usually falls under the framework of what's called high-dimensional limits. So prior to what I'll tell you about today, our understanding of the spectrum, there's been some work trying to understand the spectrum at favorite points using formal analogies between the losses of neural networks and things that come up in disordered media like stained glasses. A bit more down to earth, there's been some work on understanding the spectrum of the empirical Hessian at random starts, at initialization. But our goal today is to try to understand the spectrum along training. So at a very high level, what we show on a few different natural data models is that shortly into training, what will happen is that if you look at sort of the principal blocks of the Hessian, I'll explain what I mean by that, then there will be some deterministic number of outliers that will come out. The number of outliers will depend explicitly on the number of hidden classes in the problem. Online SGD will quickly find and put most of its mass in these principal eigenspaces. And then, interestingly, in the multi-layer setting that we'll focus on, this alignment will happen within each layer in a non-trivial way. And in particular, if your evolution starts approaching suboptimal classifiers, the spectrum will also start to show some sort of degeneracy. So today, what I'll do is I'll explain our results on a very sort of canonical problem for machine learning. It's a high-dimensional mixture model analog of the famous XOR problem. So the data model is as follows. It's a supervised learning task. I'm given a binary label, 0 or 1, orange or blue. And then what will happen is I'll get a sample. If I get a 1, then I'm getting a sample of a d-dimensional vector. Think of d as being large, like 1,000 and 1,000. And this vector will be a sample from a symmetric binary Gaussian mixture model with mean mu or minus mu, and a fixed variance. And if you get orange, you get our label is 0. Then you get a sample from nu or minus nu, where mu and nu are orthogonal, right? So the issue with this problem is, of course, its decision boundary is nonlinear. It's an x. It's not a plane. So this is arguably one of the simplest solvable statistical models where you can actually understand that you actually need a 2-layer network to solve. In particular, you can show that if the following very simple architecture can at least express the Bayes classifier. So what it is it's a 2-layer network where the hidden layer width we'll call k. We'll think of it as a fixed order 1 quantity. And so the way it works is you take your data in dimension d, you hit it against a weight matrix W, which is a k by d matrix. You pass this through an activation function. For concreteness, we'll take this activation function g to be ReLU. You hit that with your next layer weights v, which is a k-dimensional vector, and then you finally pass it through your final activation function, which we'll take today to be sigmoid. And then, okay, so now you have your architecture. You can check that as soon as k is at least 4, the Bayes classifier is expressible by this architecture. Then how do we train it? So we'll train it using online stochastic gradient descent with a fixed step size. And as loss, it's a binary classification problem, so we'll take the binary cross entropy plus a quadratic penalty to deal with coercivity issues. So in this regime, you can develop, using sort of recent works, you can develop the phase portrait even in the high-dimensional regime, using recent results of in collaboration with Gerard and Reza. The phase portrait's really non-trivial. I'm happy to explain it offline. There's degenerate diffusions pop up, conversions to suboptimal classifiers. But what I wanted to talk about today is the evolution of the spectra. And so specifically, I'll be interested in 2 natural objects. The first, I'll look at the Hessian of the empirical risk. So you take your loss, look at the empirical risk. I'll focus on the test data since we're in the online world. We have similar results for the training data. I'm happy to explain offline. So you can compute the Hessian of the empirical risk. Another thing we thought about as well, SGD is a first order method. It would be nice if you had something about first order type matrices, so eventually towards the goal of developing like spectral rules for early stopping. And so what we decided to focus on was this matrix we call the G matrix. It's the empirical second moment matrix of the gradient of the loss. In the case that the loss is a lot of likelihood, you can think about this as like an empirical Fisher information. And the same results will hold for both of these. And so what we're going to do, though, is we're not going to think about the Hessian of this huge beast. We're going to think about the Hessian within blocks. So what do I mean by this? You can think about the final layer weights, V, and we can think about derivatives just in the direction of V. That'll give you one K by K block. Then for the first layer weights, for each of the K first layer weights, you can think about derivatives in the direction of each of the sort of K d-dimensional rows. That will give you K different d by d blocks. And we'll say something about the spectral theory of each of these blocks. So to state my theorems, I need one sort of definition. I'm going to be saying over and over again, some vectors align with some vector space up to some error. What I mean by that is if I take the vector, project it into this vector space orthogonally, and look at the norm of this projection to the total norm of the vector, that's nearly 1 in a quantitative sense. So our first result, it's a lot of words, but I'll say it informally. It's you take online SGD, training this model with step size 1 over the dimension, with random initializations, then under some conditions, like the variance is small enough, and you have at least linearly many samples, then for any error level you want, after a linear burn-in period in the dimension, if you take any of these first layer weight vectors, they're vectors in dimension D is very large, it will live in a 2-dimensional vector space. And this vector space is the principal top 2 eigenspace of the corresponding Hessian. If you look at the final layer of weights, this will be some K-dimensional vector. K is moderate, like 20, 30. It'll live in a 4-dimensional vector space, which is the span of the top eigenvalues, 4 eigenvalues of the corresponding Hessian. And where does 4 come from? Even though XOR is a binary classification task, there are actually 4 hidden classes, one for each of the different modes. So here is a plot of this. Let's just focus here on the left. This is a plot in 1,000 dimensions with hidden layer size 20. This is a plot of each of the rows of the weight matrix in the first layer, and its alignment with its corresponding top 2 eigenvalues of the Hessian. Down here, I've done the same thing with the final layer weights, and its correlation with the top 4 eigenvectors of the corresponding Hessian. What you see is that it starts at initialization, everything's exchangeable, so it starts from 0, but very rapidly you have alignment. So that's alignment. So then the question is, what can we say about these principal eigenspaces? Sort of very informally, what you can show is the following picture. So at the first layer, things are fairly natural. You have 2 outliers, and the eigenvectors live in the span of the class means up to some error, and the remaining eigenvalues are quantitatively small. The second layer is where things start to get interesting. You'll have at most 4 outliers, and the corresponding eigenvectors will live in a space that will evolve along the training trajectory. What you do is you take each of the 4 class means, you look at its image under the first layer matrix, under the first layer transformation. So you do this nonlinear transformation of the means. You have this 4-dimensional vector space evolving along the training, and the eigenvectors will live in this space. And again, the remaining eigenvalues will be quantitative. So here's just a quick doodle of this, what's going on in the second layer. Again, near initialization, they all start small. And then after a burn-in period, you have 4 eigenvalues popping out of the bulk, reminiscent of the sort of famous BBP transition. But the last word I just wanted to mention is, so we had hoped that this would give you some natural spectral sort of stopping rule. But the danger is that the spectrum of this, it can be shown that in these models, the dynamics will reach suboptimal fixed points very rapidly. And when you approach these very suboptimal saddles, the degeneracy of the corresponding classifier is mimicked in the degeneracy of the corresponding spectrum of what you see. So if your classifier starts missing some of the hidden classes, then the number of eigenvalues that you start missing also changes. Thanks for your attention.